Hi folks, this is a question that's been requested. It's the question 21 from the 2012 PAT. And I've dropped this into the OneNote, so the whole paper is actually in there should you wish to have a look at it. It's a question about essentially kind of orbital stuff, or gravitational stuff more appropriately. I have had a quick look through it and I think I know how to do most of it, so I'll go through the different bits of it now. The story here is that we have a meteoroid of mass m on a circular Earth orbit, radius r. So let's just crack that out. Here is there we go, that's that bit, and then let's have planet Earth in the middle of that as well. Yeah. So there's planet Earth, and here is this meteor's orbit that is of radius r, and we're told that r is large. It is greater than 2 times the radius of planet Earth. So this first part, derive an expression for the meteoroid's speed, stating the meanings of all symbols used. This is a pretty standard question type. So an object in orbit is traveling with some speed v at a radius r. The only force acting here is gravity, so we can describe the force on it using the gravitational equation, where capital M here is the mass of Earth and g is the gravitational constant, Newton's gravitational constant, which is 6.67 times 10 to the minus 11. R is the radius of the orbit. Actually, I can just in this case use capital R because we're given that. M is the mass of the meteoroid, sorry. It's only a meteor when it actually hits the planet, isn't it? Once it's in the atmosphere, it's a meteor. That's the only force acting, so that must provide the centripetal force. Centripetal acceleration is given by v squared over r, and by F equals ma. Therefore, centripetal force is given by mv squared over r. So I can just equate the two, because gravity is the only force acting here. So mv squared over r equals gmm over r squared. Yeah, cancel the r with the r squared, cancel the small m, and get this expression then for v, square root of gm over, I should use that capital R here, where v is the speed. So that's the first part of the question done. I suspect that wasn't really the difficult aspect of this. That is a very standard question type. So I'm just going to slide that up a little bit so it's out of the way. Okay, the second part of this question is much more fiddly. Another meteoroid of the same mass in the same orbit in the same plane, rotating in the opposite direction. Okay, so there's my first meteor. Here is my second meteoroid. It has to be traveling at the same speed for it to be at the same radius. It has to. And they're going to collide head on and coalesce. They're going to join together at some given angle. Now this phrase, don't worry too much about this. This is just a phrase that refers to sort of spherical coordinates. So if you spotted an object in the sky, this angle is the kind of horizontal angle of that object. So you would have like an elevation and you could clock it around from some horizontal direction, and that's all that means. So what this first part of this question actually freaks me out a bit. It says, sketch the complete trajectory of the newly formed double mass meteoroid, showing how this angle depends on the distance r. So when these two collide, let's say they collide here, to form a single meteoroid of mass 2m. Because they both have the same initial mass, it says they have the same mass, and we're traveling at the same speed in opposite directions. When they collide, this combined meteor becomes stationary. It has to. Conservation of momentum. The momenta of the two meteoroids are equal and opposite. So when it combines, zero momentum. So this is stationary. So what it's going to do is just fall straight towards Earth. It's going to start stationary and it's going to plummet towards Earth. So from this location, it is going to fall directly towards the center of planet Earth. Therefore, this angle is constant. There can't be a change in that angle because the object is stationary in the sky effectively. It's just, it would be getting bigger as you looked at it, but it wouldn't be moving because it's falling vertically. I mean, you could argue that from some point on the surface of the Earth, if we were measuring from this point, technically the angle is changing as it's falling. But, you know, this isn't worth very many marks. There's 6 for this entire question, and we're not given a point on the Earth from which the angle's being measured. And additionally, this diagram suggests that the angle's being measured from the center of the Earth. So it can't change. So I'm not really sure what this question wants me to sketch here. Sketch the complete trajectory. I'm not really sure what they want. I mean, it's going to fall vertically. So showing how the angle depends on the distance r. Well, it doesn't. The angle is constant and doesn't depend on r at all. I mean, if you really wanted to sketch the relationship between is that a psi and r, it would be a very dull graph indeed, because it's just flat. That is a constant as far as I can see. So that's that bit. Sketch the kinetic energy. This is more interesting. And the expected surface temperature. We'll leave the surface temperature for a moment. Let's think just about the kinetic energy. And we're going to have to give us some sort of explanation. So notice that we're going to be going from a distance r that is equal to the initial radius of the orbit, which was greater than 2re, to distances r that are much less than 2re. So and presumably we're going to have to sketch this right up till the point of impact at re. So let's have a careful think about what's happening. The first thing to note is my combined meteor is basically going to be turning gravitational potential energy into kinetic energy. So what we've got to think about is how much gravitational potential energy does it start with, and in what way is that changing as it falls. Gravitational potential energy is given by this equation. Notice that it's negative. So this again is the mass of Earth, this is the mass of the meteoroid, and r is the distance in between the center of Earth and the center of the meteoroid. And this is negative. What we can say is that the kinetic energy is equal to the change in GPE, and actually minus the change in GPE, if you like. The reason I can say that is by conservation of energy, I could write that delta EK plus delta GPE must be equal to 0. That's just conservation of energy, isn't it? The change in this plus the change in this must be equal to 0. Therefore, the change in EK must be equal to minus delta GPE. Since the initial kinetic energy is 0, I can get rid of the delta here. The total kinetic energy must be equal to this. So change in GPE is final minus initial. So that is minus final GPE minus the initial GPE. So the final GPE at any given time is that minus the initial GPE. There's going to be a lot of minus signs here, which was this. So minus signs fly in, really. That is therefore equal to G over R minus G over R. Oh, sorry. That'd be weird. So that's the expression for the kinetic energy. We only have to sketch this. We've only got to give it a sketch of it. This is a constant. All of those numbers are not changing. This, however, little r starts at big R and then gets progressively smaller. So this term is getting larger and larger the whole time. So our EK starts from 0 when little r is equal to capital R, but then this term gets bigger and bigger as little r gets smaller and smaller until it gets to the limit of RE. So what we can say then is that the kinetic energy, what's it going to look like? It's going to look roughly proportional to 1 over r, roughly, something like that. It's going to have a kind of 1 over r sort of shape to it. So what does that look like? Well, 1 over r is something, oh my goodness, this is hard to draw using one of these like weird tablet-y things. That's a 1 over r curve, as you can see, bit miserable. But there's a problem here, because that would be the kinetic energy curve if there was no if there were no issues with things like atmosphere, etc. But the question actually makes reference to this. Look, for R less than 2RE, effects due to the Earth's atmosphere cannot be neglected. So once we get into the Earth's atmosphere, which it's suggesting is at about 2RE, I don't know about that, but anyway, that we can no longer neglect the effects of the Earth's atmosphere. And that's pretty high up, 6,400 kilometers up. The Earth's atmosphere is pretty thin. So what we'll find is, rather than this kinetic energy increasing at this sort of increasing rate as R decreases, so R starts, we start with 0 kinetic energy, sorry. I need to draw this better. Oh my goodness, that is not better. Neither is that. This is real. Why is this so difficult? I would have been better with a touchscreen. So that's my 1 over r curve. This is the point R. That's my initial. This axis is R. This is EK. So that's what my curve starts to look like. But then something interesting is going to start happening once I'm within, this is the kind of 2RE limit, and then somewhere here, let's put the RE limit. This is where it hits the radius of the Earth. My graph has to stop there because the meteor has crashed into the surface. But in this zone, air resistance is going to be an increasing factor. So you can well imagine that this meteor is going to achieve some sort of terminal velocity in the atmosphere, and at terminal velocity V becomes constant, and therefore kinetic energy must become constant. So in this region, my graph needs to sort of level out. I don't really know the exact shape of it. This is, after all, just going to be a sketch. So something like that. Where this kind of represents some sort of terminal velocity. So hopefully that makes sense, I think. Yeah, so outside of the Earth's atmosphere, it's just a direct transfer from gravitational potential into kinetic. Inside the Earth's atmosphere, basically, something different has to happen. The resistive forces due to the atmosphere are going to cause a terminal velocity. So with that in mind, let's think about the surface temperature, because if it's reached a terminal velocity but it's still losing gravitational potential energy, where is that energy going? Well, it's heating up the meteoroid. So in terms of surface temperature, post-collision, I don't know if we need to take that into account. Post-collision, the surface temperature is going to be high. So at R, here's R, this is temperature now against, that's pretty wild T. This is R, the temperature is going to start at some value. As R decreases, here's 2RE, that's where the atmosphere starts, and then here's collision point RE. As it falls through space, the surface temperature isn't going to change at all. There's no reason for it to change. But once it enters the atmosphere, it's going to start getting hot. So what if we think about this graph, what's going to happen is the temperature is going to start heating up. At this point, at terminal velocity, we're converting potential energy directly into heat, basically internal energy on the surface of the meteor, because we're no longer gaining velocity. So in this region where it's reached terminal velocity, we would expect this graph to have that 1/r shape, some kind of 1/r shape to it. Because here we're converting gravitational potential directly into heat. In this in-between bit, this is a slightly trickier bit to kind of think about. I'm not sure really what sort of marks would be available here. It's hard to tell, I think, whether or not the meteor is going to slow down when it enters the atmosphere. I'm not sure we've got enough information. You know, in my graph here, it hasn't. So I think I have to make sure my graphs match each other. So given that it doesn't slow down, we're at no time are we sort of converting, at no time are we converting kinetic energy into heat. So I think my 1/r needs to kind of come from there and look a little bit like that. So that's what I would go with. You know, there's a lot of factors to this, and it's impossible to say exactly what either of these graphs would look like. You know, there is an argument that as it enters the Earth's atmosphere, it'll actually slow down. Maybe it's already traveling well above terminal velocity. Maybe it isn't. It's kind of hard to tell without some more information about the nature of the meteor. You can't tell what that terminal velocity would be. So, and without more information about the original height that it fell from, you can't really tell whether or not it's going to slow down or not. So these two graphs I feel match reasonably well. So yeah, in terms of the question then, give a very brief explanation of why you expect the temperature to depend on R in that way. So my explanation is here, no air resistance, so no heating effect. This part, we're saying that terminal velocity, so no change in KE implies GP is changing directly into heat. Something like that. And I think that's going to get me the marks. All right, sorry, that took a little longer than planned. These things always do. But hopefully that explains the rationale and the method for kind of thinking your way through that question. Alrighty.